Hello students, today we'll be solving the IB Math AGL May 2024 paper 2 time zone 2 question number 12, that is the last question of this paper. You will be getting the other solved past paper questions of this paper and of the other papers in form of playlist on my channel NS Online Math Tutoring classes. You will also be getting playlists where the solved past paper questions will be available based on their topics. I'm Nilanjana Sanyal. I'm an online IB Math AHL level tutor. In case you want to join my classes, please contact me for more details. My phone number and my website address are displayed at the bottom of the screen. So without any further delay, let us start to solve this question number 12. The maximum mark is 21. It says consider the differential equation dy by dx minus y times cosec of 2x cosec 2x equal to square root of tan x where x is greater than 0 but is less than pi over 2 and y is equal to pi over 4 when x equal to pi over 4. Subpart A is saying use Euler's method with step length h equal to pi over 12 to find an approximate value of y. The Euler's method will always be giving us an approximate value of y. When x equal to 5 pi over 12 and give your answer correct to 3 significant figures. Okay, so the formulas that we'll be using for the Euler's method will be xc, the current value of x should be equal to xp, the previous value of x, plus the step size or step length h, and yc, the current value of y will be equal to ip, the previous value of y, plus the step length or step size h, times the dy by dx expression, which will be an expression containing only x or only y or both x and y. In this case, first of all, we have to rewrite this. This is a differential equation. We have to rewrite this differential equation to get the expression for dy by dx. Okay. So first of all, let me write this. This expression can contain only x or only y or both x and y. And we will be taking the previous value of x and the previous value of y, because we need to know the numerical value of this dy by dx expression. Okay. And the initial value of x is given as pi over 4 and the initial value of y is also equal to pi over 4. Okay. And let me write the differential equation first. Dy by dx minus y cosec 2x equal to square root of tan x. Okay. And we need to have the dy by dx expression. So this will be dy by dx equal to y cosec 2x plus square root of tan x. Okay. And now I can form the table. Let's see. Let's use the calculator. Let's see what values do we get first of all. So I'm using the TI Inspire CX2 calculator and we'll be going to the add lists and spreadsheet. And you can rename this column A because I'll be storing all the x values in column A. So you can name this column A as x and the column B as y, because the column B will be having all the y values. And then we come to the E1 cell and we will be storing the initial value of x, the given value of x, which is pi over 4. So it is pi divided by 4. Okay. And the initial value of y is also pi over 4. And I come to the E2 cell. over here, I will be inputting a formula. I'll be inputting this formula, okay? This part. And this is xp, the previous value of x. And where is the previous value of x stored? Previous value of x in this case is the initial value of x. And where is it stored? It is stored in the E1 cell. Okay. So I will be entering equal to, because every formula should be starting with this equal to. Okay. So it is equal to, and pi over 4 is stored in A1 cell. So I will be writing A1 plus h. H is pi over 12. Okay. This is xp plus h. So A1 plus pi over 12. Enter. Fine. It has given me a decimal value. Doesn't matter. And now I have to just go on incrementing the x value till I reach this value of 5 pi over 12. Okay. So in case you want to see the pi over 12 values, means multiples of pi over 12, I can just go to the document settings and I go to this, and over here it is exact arithmetic, it is off, turned off. I can turn it on, and you see the first one was pi over 4 and now it is pi over 3, because if you add pi over 12 to pi over 4, the common denominator is 12 and this is 3 pi and this is pi. So this will be 4 pi over 12 or pi over 3. Okay. So you are having this pi over 3 over here. Okay. And to this pi over 3, if I add, let me do it over here, the calculation. Pi over 3 to this, if I add pi over 12 one more time, this is equal to pi over 3 is 4 pi over 12 and plus pi over 12. So this is 5 pi over 12. Okay. So I have to come to 5 pi over 12 because I have to get the approximate value of y when x equal to 5 pi over 12. Therefore, I need one more row. See, it is 5 pi over 12. Okay. Now I come to this B2 cell. Again, I'll be inputting a formula. What formula should I be inputting? This is y. See the current value that we will be calculating, and this is equal to, because I'll be inputting a formula. So I'll be starting with this equal to sign, and yp, the previous value of y is stored in the B1 cell. So in place of yp, I'll be writing B1 plus h, which is equal to pi over 12 times this dy by dx expression. And in place of y, because it should be yp, I'll be writing B1, and in place of x, it has to be xp, the previous value, which is stored in A1 cell. So I'll be writing A1. Okay. So this is equal to B1 plus pi over 12. This is the, okay. Pi over 12 and times, now I'll be inputting the dy by dx expression. You can see from here. See, this is the minus sign, which when taken to this side will be changed to a plus sign. So this is y cosec 2x plus square root of tan x. Okay. So I am starting this bracket and y. So in place of y, it is B1 times cosec. So cosec is this one, 2x. So 2 times A1 and plus square root of 10, and it is xo A1. Bracket closed, I come out, and then there will be this bracket And you can see over here in this B2 cell, you cannot see the entire formula, but over here you can see B1 plus pi over 12 times B1 because it is Y times cosec 2x, so 2 times A1 plus square root of tan x, so tan of A1, okay, and enter. For this, I need to get the decimal value. So I have to again go back and I have to, rather I come to document and I have to go to number 7, settings and status. And then it is document settings number 2. And now again I turn this off. Okay. So this has also changed, but now you know that this one, the number 3 row is actually 5 pi over 12. The x value is actually 5 pi over 12. Okay. And I come down. So I will be writing the x. This one will be pi over 3. So I can start with pi over 4. When x equal to pi over 4, y is also equal to pi over 4. When x equal to pi over 3, what is the value of y? It is 1.25281. They have asked me to give the answer correct to 3 significant figures. So I am writing answers up to 3 significant figures, to correct to 3 significant figures. Okay. So it is 1.25. I am taking 1.25 instead of writing 1.25281 and all. Okay. 1.25. And finally, it will be 5 pi over 12. So this will be 1.97608. So 1.98. Okay. Correct to 3 significant figures. And this is also correct to 3 significant figures. Okay. Therefore, approximate value of y when x is equal to 5 pi over 12 is 1.98, correct to 3 significant figures. Okay. So now, subpart B, show that d dx, that is the derivative of, first derivative of half ln of cot x with respect to x, of course, is negative cosec 2x. Okay. So, first derivative with respect to x, half ln of cot x half is the coefficient, so I can take it outside of ln of cot x. It is a composite function. So this is half ln of x when differentiated with respect to x gives you 1 over x. So ln of cot x when differentiated with respect to x will be giving us 1 over cot x. Okay. When it is ln of x, it is 1 over x. Now it is ln of cot x, so it is 1 over cot x. Now we have to differentiate the cot x. And the derivative of cot x with respect to x is negative cosec square x. Okay. So this is negative half and cosec square x. So let me just change these to sine and cos and let me see what happens. So 1 over cot x is tan x. So I'm writing this as tan x. And times cosec square. Cosec x is 1 over sine x. So cosec square x will be 1 over sine square x. Okay. Equal to negative half times sine x over cos x times 1 over sine square x. And sine square x is sine x times sine x. So this sine x cancels with 1 of the sine x from the denominator. So this is equal to negative half, or I can write this as 1 over 2 sine x cos x. Okay. So this is negative 1 over 2 sine x cos x is sine 2x. So this is equal to negative cosec 2x, and we have shown this. Shown. Okay. So part C. Show that square root of cot x is an integrating factor for this differential equation. So previous part B also contained 4 marks, and this is also carrying 4 marks. Okay, so first of all, I have to write the differential equation. So let me write, I'm just copying from here. Okay, so let me write the differential equation first of all. Dy by dx minus y cosec 2x is equal to square root of tan x. Okay, the integrating factor if is e to the power of p. Okay, I can write this as a function of x dx. It can be a function of x, it can be a constant term. It is p dx. Okay, and p is what? In this case, it is minus cosec 2x. Okay, so this will be e to the power of minus cosec 2x dx. Okay, and now you see integration is just it is anti-differentiation. So the derivative of half times ln of cot x is negative cosec 2x. So the integral of negative cosec 2x should be half ln of cot 2x, cot x. Okay, because the derivative of half ln of cot x is negative cosec 2x. So the integral of negative cosec 2x has to be half ln of cot x. Okay, so equal to e to the power of half ln of cot x. Okay, ln cot x from subpart B. So this is equal to e to the power of ln and cot x raised to the power of half. This coefficient is transferred to the power part. Okay, so e to the power of ln of cot x raised to the power of half, and e to the power of ln, they will be cancelling because these two are inverse functions, and this is equal to cot x raised to the power of half or equal to square root of cot x. Okay, shown. Okay, subpart D. Hence, so we will be using this integrating factor. Hence, by solving the differential equation, show that y equal to x times root tan x. It is containing 5 marks. Okay. So, after we get the integrating factor, what do? We multiply the entire equation, all the terms, by the integrating factor. Let me write the equation once more. It is dy by dx minus y cosec 2x equal to square root of 10x. And now I am multiplying with the integrating factor, multiplying the equation with the integrating factor, we get square root of cot x and dy by dx minus y cosec 2x square root of cot x equal to square root of tan x times square root of cot x. And this can be written as square root of tan x times cot x, and tan x times cot x equal to 1, because cot x equal to 1 over tan x. If you want, I can write this. Tan x times 1 over tan x, which is equal to 1. Okay. So, the right side is equal to 1. And what is the left side? Left side is nothing but the derivative of y times root cot x. If you use the product rule, then you will be getting these two terms. How? If we differentiate this y with respect to x, we get dy by dx and the root cot x t's. And now we are differentiating the root cot x. If we differentiate the root cot x, let me show you over here. Root cot x derivative. This is cot x to the power of half. Of course, the derivative of this. So the power will be coming down and it will be cot x to the power of half minus 1 is minus half. So you will be having 1 over root cot x, and this will be minus. If you differentiate cot x with respect to x, you will be getting minus cosec square x. And most probably I have shown you this one, minus cosec square x, and this time you are having the root cot x. Previously you had the cot x. Okay, let me show you. I don't have space. I am just coming over here. Okay, so it is, these two are getting multiplied. So it is negative half and 1, it is 1 over root cot x, and it is cosec square x, so it is 1 over sine square x. And I am seeing that there is the root cot x in the numerator. So let me multiply the numerator and the denominator by root cot x. So, and if I multiply the denominator by root cot x times root cot x will be cot x times 1 over sine square x. And 1 over cot x, this is root cot x times 1 over cot x, which is tan x. So this is half root cot x, and tan x, in place of tan x, I am writing sine x over cos x. and there should be the 1 over sine square x. So I am not having any space on the right hand side. I am writing over here. And this one and this one will be getting cancelled. And again, you are seeing you are having 2 sine x cos x. So 1 over 2 sine x cos x is 1 over sine 2x or cosec 2x. So you are having minus cosec 2x and square root of cot x. So you are seeing minus cosec 2x and square root of cot x, and there is the y. Okay. So you do not have to show all these things. In case you are confused that how can I write this in place of these two terms, I have shown you the derivative. How am I getting this? If you use the product rule to this, if you apply the product rule, you get back these two terms. Okay. But definitely you don't have to show all these. Always remember, whatever you are getting as the integrating factor, it will be d dx of y times the integrating factor. Has to be every time. Okay. And the right hand side is equal to 1. See, this is equal to 1. Okay. So now we will be integrating both sides with respect to x. Dx, it is 1 dx. And it is y root cot x equal to x plus c. There should be the constant of integration, and we know that when x equal to pi over 4, y equal to pi over 4, we have to get the value of c. When x equal to pi over 4, y equal to pi over 4. Okay, so we have to get the value of c. So pi over 4, therefore pi over 4 and cot pi over 4 equal to pi over 4 plus c. Okay, and cot pi over 4 is 1 over tan pi over 4. Tan pi over 4 is 1. So 1 over 1 is 1 and square root of 1 is 1. So this is pi over 4 times 1 is pi over 4 equal to pi over 4 plus c. So implies c is equal to 0. Okay. So therefore, y times square root of cot x is equal to x, or y equal to x over square root of cot x, which is x over square root of 1 over tan x, which is x times square root of tan x. Okay. So the question was, show that y equal to x times square root of tan x. Therefore, y is equal to x times square root of tan x. Shown. Okay, subpart E. Consider the curve y equal to x times square root of tan x for x greater than 0 but less than pi over 2, and the Euler's method approximation calculated in part A. For Euler's method approximation, when x was equal to 5 pi over 12, the approximate value of y was found to be 1.97608, and there are other digits also after 8. Now coming to I, the first subpart of subpart E. Find the y coordinate at x equal to 5 pi over 12 using this expression. Give your answer correct to 3 significant figures. Okay. So y equal to x times square root of tan x when x equal to 5 pi over 12, y is equal to 5 pi over 12 times square root of tan 5 pi over 12. Okay. So this should be equal to, I have to go to the calculator. I need the calculator page, and it is 5 pi over 12 times square root of tan of tan. The angle is 5 pi over 12. Okay. It is 2.528. I am taking 2.53 correct to 3 significant figures. Okay. 2.53 correct to 3 significant figures. Okay. Now coming to the second subpart II, by considering the gradient of the curve, suggest a reason why the Euler's method does not give a good approximation for the y coordinate at x equal to 5 pi over 12. Okay. So let us see the curve. It is paper 2. We can sketch, we can graph it. So I need another page, the graph page. Okay. It is x times square root of x, tan x. Tan x. Okay, enter. Fine. And I need from 0 to pi over 2. So menu, number 4 window zoom, and number 1 window settings. And it is 0. Let me take it as -1 because I always want to see the y-axis. So I'm keeping it as -1, and it is pi over 2. So pi divided by 2. This is the exact value I am taking. Or let me also, it is pi is 3.14159, and all divided by 2, it will be 1.57 something. So let me take it as 1.75. Okay, let's see what happens. Now you see there is this single thing, and at pi over 2, tan pi over 2, you have the asymptote. Okay, at pi over 2. So I can just draw this, try to draw this. You just give a rough sketch because this will be containing just a single mark. You see, the subpart E is carrying 3 marks. So one for the subpart I, one for the subpart II, and finally the final one for the subpart III. Okay. So you just give a rough sketch. Now you see, this is the graph that I have drawn. I can show you the calculator. This is the graph that we have found using the calculator. And if I use the trace, graph trace feature, it is number 5 trace and number 1 graph trace. Okay, it is, let me just check. It has already spotted a point, but let me check whether the x value is equal to 5 pi over 12 or not. I'm just entering the 5 pi over 12 x value. So it is 5 pi divided by 12. Enter. Okay, so previously I was testing. Okay, so this is the place, this is the point actually. And over here you see the curve is concave up, and it is having a very rapid change in the gradient in this part. In the locality, in the neighborhood of x equal to 5 pi over 12, the curve is bending a lot. So the gradient will be changing very rapidly. And for the Euler's method, it just depends on the gradient, the dy by dx value. So we will be starting from x equal to pi over 4, somewhere over here, anywhere below, before 5 pi over 12. And then we will be just moving in a linear way, plus h. The increment is plus h. So it is a linear advancement. Okay. So And over here you are seeing it is bending a lot. So the curve is bending a lot. So the gradient will be changing very rapidly. Therefore, it is not a good approximation. So you give this graph and you say the reason as since the curve is rapidly changing its gradient, near x equal to 5 pi over 12. Therefore, it is the Euler's method. Let me write it over here. The Euler's method does not give a good approximation for the y coordinate. It is containing just a single mark. We have drawn the graph and we have written this line. It is more than enough. And actually, this is the reason. The third subpart, I state why this approximation is less than the y coordinate at x equal to 5 pi over 12, because the actual y coordinate will be 2.53 correct to 3 significant figures. It will always be giving you a lesser value when the curve is concave up. And over here you see the curve is having a concavity upwards. So positive concavity. So therefore the Euler's method is giving us a smaller value. Okay. Since the curve is concave up for therefore the Euler's method gives us a smaller value. If the concavity is downwards, then the Euler's method will be giving us values which will be more than the actual values. Okay. So this is the answer for all the three subparts of the subpart E. Finally, it is the subpart F. By considering dy by dx minus y cosec 2x equal to square root of tan x, deduce that the curve y equal to x root tan x has a positive gradient for x is greater than 0 but is less than pi over 2. Okay, so the dy by dx expression will be y cosec 2x plus root tan x. Okay, because when we had solved this differential equation, we had found this solution, y equal to x times root tan x. So obviously the gradient has to be this expression. Okay, so for x greater than 0 but less than pi over 2, over here it is 2x. So 2x should be greater than 0 but should be less than pi. 2 times pi over 2 is pi. Okay. And we are seeing that there is this y. How to deal with this y? We can substitute this expression in place of y. In place of y, we can write x times root 10x, because otherwise, how do we say that what value of y will we be having? Okay, because we have to show that dy by dx will be always positive, will be having a positive gradient, means dy by dx value should be a positive number. So we do not know anything about the y value. So how can we get the y value? We will be substituting x times root 10x in place of y. Okay. So since y equal to x times root 10x, therefore dy by dx is equal to x times root 10x times cosec 2x plus root 10x. Okay. Since x is an angle from the first quadrant, or is an acute angle, therefore tan x, I can write over here, tan x is greater than 0. Because x is an angle from the first quadrant, tan x has to be greater than 0. Tan of any acute angle is a positive number. And for cosec 2x, I have written this. Okay. 2x is an angle from the first two quadrants, from the first quadrant or the second quadrant. Therefore, cosec 2x, cosec is 1 over sine, and sine is positive in the first two quadrants. So, cosec is also positive in the first two quadrants. Cosec x is greater than, cosec 2x is greater than 0. Therefore, cosec 2x is greater than 0. Okay. And x is also, x is between 0 and pi over 2. Therefore, x is greater than 0. So, x is greater than 0, tan x is greater than 0, and cosec 2x is also greater than 0. Hence, dy by dx is greater than 0. Or, what is the question? Has a positive gradient. Okay. Or, the curve has a positive gradient when x is greater than 0 but is less than pi over 12, pi over 2 rather. Okay. So this completes our answering of this question number 12. Thank you for staying with me till the end. Please like and share this video with your friends if you have liked my explanation. And please do not forget to subscribe to my YouTube channel in case you have not subscribed to my channel till now. Your liking, sharing, and subscribing will be motivating me, and it will be telling the YouTube that my video is worth watching. So the YouTube, it will be increasing the reach of my video. The YouTube will be knowing that my video can be shared to more number of students. It is worth watching. So that will be helping me a lot. And from our next session, we will be starting to solve a new paper, and we meet very soon. Till then, bye.